So now I am going to discuss the solutions for the questions in the assignment in center of mass and conservation of linear momentum, starting from question number 31. Look at the question number 31 on the screen. A trolley of mass 360 kg is lying on a horizontal frictionless surface. A man of mass 40 kg runs with uniform speed on the trolley by a distance of 2 meters in 0.1 seconds. What is the velocity of the trolley relative to the earth? So here we consider the trolley and the man together as one system. So here weight of the system is balanced by the normal reaction force on the trolley by the frictionless surface. So there is no external force acting on system. Therefore, momentum of system remains constant. The final momentum of system of the man and trolley after the man begins to walk on the trolley will be equal to the initial momentum system. Pi bar is the initial momentum system of the man and trolley that can be taken as 0 bar, because initially both the man and trolley are at rest. So final momentum of the man and trolley is vector sum of the momenta of the trolley and the man. So here P1 bar is the momentum of the trolley, P2 bar is the momentum of the man. So you can write here P1 bar is equal to minus P2 bar. That means when the man starts moving on the trolley in one direction, the trolley starts moving in the opposite direction with the same magnitude of linear momentum. So in vector form we can write M1 V1 bar equal to minus M2 V2 bar. Here V1 M1 is the mass of the trolley, that is 360 kg. M2 is the mass of the man, which is equal to 40 kg. V1 bar is the velocity of the trolley with respect to stationary observer on the earth. V2 bar is the velocity with which the man walks on the trolley. You can observe that the negative sign implies that the velocity of the trolley relative to the earth is opposite to the velocity of the man relative to the earth. That means with respect to stationary observer on the earth, the man and trolley move in opposite directions. So that means when two bodies move in opposite directions, magnitude of the relative velocity of one body with respect to other body will be equal to ordinary sum of the magnitudes of the velocities of the two bodies. If you substitute here M1 equal to 360 kg, M2 equal to 40 kg, you get V2 bar equal to minus 9 times V1 bar. So relative velocity of the man with respect to the trolley is equal to V2 bar minus V1 bar. So VREL bar means relative velocity of the man with respect to the trolley. We can also write V bar subscript 2 comma 1. That is minus 9 V1 bar minus V1 bar. So relative velocity of the man with respect to the trolley is equal to minus 10 V1 bar. If we take magnitudes here, so magnitude of the relative velocity of the man with respect to the trolley is equal to 10 V1. So V1 can be written as magnitude of the relative velocity by 10. Magnitude of the relative velocity is equal to 2 meters by 0.5 seconds. It is given that the man walks 2 meter distance distance on the trolley in 0.5 seconds. That means the distance 2 meters is covered by the man relative to the trolley in 0.5 seconds. So magnitude of the relative speed of the man with respect to the trolley is equal to distance covered by the man relative to the trolley divided by time interval. So you get V1 equal to So V1 equal to get 0.4 meter per second. That's the answer. This problem was originally given in one of the previous MSET examinations, but initially it was given similar question in one of the All India entrance exam papers also. If you want to copy the solution of this problem, you can take a pause and copy the solution of the problem. So for question number 31, which I have just now discussed, the second option is answer. Next, I am going to discuss the next question. That is question number 32. Look at the question number 32 on the screen. Two particles of masses m1 and m2 in projectile motion have velocities u1 bar and u2 bar respectively at time t equal to 0. They collide at time t naught. Their velocities become v1 bar and v2 bar at time t naught, at time 2t naught, while still moving in air. The value of modulus of m1 v1 bar plus m2 v2 bar minus m1 u1 bar plus m2 u2 bar is. This question was originally given in one of the previous screening test papers of IIT JEE exam, but it is within the scope of the other entrance examinations also. Now m1 v1 bar plus m2 v2 bar gives you the total linear momentum system of the two particles of mass m1 and m2 at time 2t naught. m1 u1 bar plus m2 u2 bar gives you the total linear momentum system of the two particles at the initial instant t equal to 0. Now the total linear momentum system of the two particles will not be changed due to the internal forces within the particles of the system. The total linear momentum system of the particle changes only external forces acting on system. So in this case, the external force on system is the force of gravity. So net external force on system is equal to total weight of the two particles m1 plus m2 into g. Therefore, that m1 u1 bar plus m2 u2 bar, that gives the total initial amount of system, which can be denoted by pi bar. m1 v1 bar plus m2 v2 bar gives the total final amount of system at time t equal to t naught. So you're asked to find magnitude of the change in linear momentum system in the time interval 2t naught minus 0. That means in the time interval 2t naught. So Pf bar is the final momentum system at the instant of time t equal to t naught. m1 u1 bar plus m2 u2 bar gives the initial momentum system at the instant t equal to 0. So you are asked to find the change in the linear momentum system of the two particles in the time interval 2t naught minus 0 or 2t naught. So change in the linear momentum system of the particles is equal to impulse of the external force on the system. The external force on the system is the force of gravity, which can be assumed to be constant at the given place. So external force on the system is equal to m1 plus m2 into g into time interval. So the time interval delta t equal to 2t naught minus 0. So you get the answer as 2 into m1 plus m2 into g into t naught. So third option is answer for this question. If you want to copy the solution, you can take a pause and copy the solution. See the question number 33 here. Next question. A man of mass small m clings to a rope ladder suspended below a balloon of mass capital M. The balloon is stationary with respect to the ground. The man begins to climb the ladder at a speed v with respect to the ladder. In what direction and with what speed with respect to the earth will the balloon move? What is the state of motion after the man stops climbing? This problem is similar to one of the special cases I have discussed, where a man is initially at rest begins to walk on a trolley or a boat floating in still water lake. Similar discussion applicable here also. Instead of boat you have balloon, that's the only distinction. Here we assume that the mass of the ladder along with the balloon is capital M. The mass of the balloon along with the ladder is capital M and the mass of the man is small. So we consider the man of mass small m and the balloon along with the ladder with mass capital M as one system. That is, total mass system is capital M plus small m. Initially the man is at rest, balloon is at rest. That means you may assume that total weight of the system is balanced by the upward force of buoyancy. So due to large size of the balloon displaces large amount of air, due to which it experiences a force of buoyancy in the upward direction. So the total weight of the system of the man and the balloon is balanced by the upward force of buoyancy. Therefore, we can say that net external force on system is 0. Therefore, velocity center of mass of system remains constant. The velocity of the center of mass of the system remains constant. Initially, both the man and the balloon are at rest. So initial velocity of balloon is 0, initial velocity of man is 0. So we can say that initial velocity center of mass is 0. And velocity center of mass of system remains constant. That means velocity center of mass will remain constant at 0. Therefore, center of mass of system of the man and the balloon is at rest. And total momentum system of the man and balloon is equal to total mass of system and velocity center of mass system. Here velocity center of mass system is 0, therefore total momentum system is 0. So when the man begins to move in the upward direction with respect to stationary observed on the earth, with respect to stationary observed on the ground, the balloon starts moving in the downward direction. That means for the first part of the question, the balloon starts moving downwards with respect to observed on the ground. That means V1 bar is the velocity of the man with respect to station observed on the earth. Let V2 bar denote the velocity with which the balloon starts moving with respect to station observed on the earth. Here resultant amount of system of the man and the balloon is 0. That means the vector sum of momentum of the man and momentum of the balloon is 0. The vector sum of the momentum of the two masses becomes 0 when the two masses are either at rest or they move in opposite directions with the same magnitude of linear momentum. So when the man is at rest, balloon will also be at rest. The man begins to walk upwards with some momentum along the ladder. Then balloon starts moving downward with the same magnitude of momentum. That means they both of them, balloon, man and balloon, remain either at rest or move in opposite direction with same magnitude of momentum. Therefore, when the man stops walking on the ladder, that means when the man stops moving with respect to station observed on the earth, the balloon also stops moving. So now the two velocities are in opposite directions. So momentum of the man is equal to mass of the man into velocity of the man, which we denoted by V1 bar. Momentum of the balloon is equal to mass of the balloon into velocity of the balloon. That means the negative sign indicates that the two velocities are in opposite direction. Here V is the velocity, measure the velocity of the man relative to the ladder, means relative to the balloon. That means the relative velocity of the man with respect to the balloon, we can write V1 bar minus V2 bar. That you can write it as V bar. The relative velocity I have denoted by V bar. Relative velocity of man with respect to ladder or balloon. Now solve these two equations 1 and 2. You are asked to find V2 bar here, velocity of the balloon. For that you have to eliminate V1 bar. From second equation you can substitute the value of V1 bar into the first equation. Now we can take a pause and copy the solution of the problem up to this and simplify the equations 1 and 2 and solve for V2 bar. Here I have solved the problem completely in vector form. So you get V2 bar equal to, that is velocity of the balloon with respect to stationary observer on the earth, minus small m into V bar by capital M plus small m. The negative sign implies that the actual velocity of the balloon with respect to stationary observer and that is opposite to the velocity of the balloon relative to the actual velocity of the balloon with respect to stationary observer on the earth is opposite to the relative velocity of the man with respect to balloon. The man moves upwards with respect to balloon, balloon moves downwards with respect to stationary observer on the earth. So if you consider only magnitude, negative sign can be omitted. So V2 can be written as small m into V by capital M plus small m. So that's the answer for first part of the question. Small m into V by capital M plus small m in the downward direction. But when in the part B of the question, that means the man stops climbing the ladder, the balloon also stops with respect to stationary observer on the earth, because the resultant motor system of the two masses is 0. In case you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. Look at the next question, question number 34. Block of mass small m is placed on the top of a bigger block of mass capital M as shown. All the surfaces are frictionless. The system is released from rest. Find the distance moved by the bigger block at the instant the smaller block reaches the ground. Here we consider the two blocks as one system. When you consider the two blocks as one system, the external forces acting on the system are total weight of the system, which acts downwards, and Normal reaction force by the floor on the bigger block of mass capital M. When you consider the two blocks as one system, then the contact force on one block by the other block should be considered as the internal force. And internal forces play no role in the motion of center of mass of system. So when you consider two blocks as one system, the external force acting on system is total weight of system and normal reaction force by the floor on the bigger block of mass capital M. And these external forces are in the vertical direction. Therefore, these forces have no component in the horizontal direction. That means the horizontal component of the external force on the system is 0. I choose the horizontal direction as x-axis and vertical upward direction as positive axis. So the horizontal component of the external force on the system is 0. Therefore, the horizontal component of the linear momentum system remains constant. Initially, both the blocks are at rest, so initial momentum system in the horizontal direction is 0. Therefore, final momentum system in the horizontal direction will also be 0. That means in the horizontal direction, the two blocks move in opposite directions, the same magnitude of momentum. That means if the smaller block is shifted towards left side horizontally when it reaches the floor, ground, the bigger block will be shifted towards right, because the resultant moment in the horizontal direction is 0, as the horizontal component force on system is 0. Therefore, the position of center of mass of system, velocity of center of mass, I mean x component of the velocity of center of mass of system remains constant. Initially, both the blocks are 0. Therefore, initial velocity of the x component of center of mass is 0. Therefore, final velocity of the x component of center of mass will also be of the system will be 0. Therefore, there will be no displacement for center of mass of system of the two blocks in the horizontal direction. Therefore, if you choose some fixed point on the ground as origin, for example, if you choose the initial position of the bottom of the bigger block as origin of coordinate system, then here, or you can also choose origin somewhere else to the left side also, some fixed point on the floor. The next coordinate center of mass remains C. If you choose the horizontal direction x-axis. So here the first mass we write x coordinate center of mass system with two mass m1 m2, you can write m1 x1 plus m2 x2 by m1 plus m2. New value of the x coordinate center of mass system of the two mass, you can write m1 x1 dash plus m2 x2 dash by m1 plus m2. So m1 plus m2 can cancel. So here you can write m2 into x2 dash minus x2 is equal to m1 into x1 minus x1 dash. So x2 is the distance of horizontal distance of center of mass. So let me choose m1 as equal to small m here, m2 equal to capital M. So x2 dash. Now this we choose some fixed point on the ground to left side of both the blocks as origin of coordinate system. Suppose as the block, when the smaller block reaches the ground, bigger block moves towards right side from conservation momentum principle. Therefore, horizontal distance of bigger block from origin will increase. x2 is the initial distance of the center of mass of the bigger block from origin. x2 dash is new distance of center of mass of bigger block from origin. So that will be x2 dash minus x2 gives you the horizontal displacement of the bigger block from the origin. I mean horizontal distance. So with a bigger block moves, I denote it by S2. S2 is the magnitude of horizontal displacement of the bigger block of mass capital M. And similarly, x1 minus x1 dash gives you the horizontal distance moved by the first mass m1 towards left side. The first mass m1 is coming nearer to the origin. That means x square and the first mass will decrease. Therefore, x1 minus x1 dash gives you the horizontal distance moved by the first mass. I denote by s1. So s1 is the horizontal distance moved by the first mass when it reaches the ground, as seen by stationary observer on the ground. S2 is the horizontal distance moved by the second mass towards right with respect to stationary observer on the ground. Here m2 equal to capital M, m1 equal to small m. So when the smaller block reaches the ground, the horizontal distance which a smaller block moves towards left relative to the bigger block is equal to L. The horizontal distance through which the smaller block moves towards left side relative to bigger block will be equal to L, because the two horizontal displacements of mass m1 and m2 are in opposite directions. So magnitude of the relative displacement, smaller block relative to the bigger block, can be taken as some of the magnitudes. I mean magnitude of the relative displacement of smaller block relative to bigger block, I mean in the horizontal direction only. That is equal to L. Now you can solve these two equations to find S2. You are asked to find distance S2, that is distance moved by the bigger block, actual distance moved by the bigger block with respect to stationary observer on the ground. So you have to solve from this. So you can solve it yourself. If you want to copy the solution of this problem, you can take a pause and copy the solution of this problem. So you get S2 equal to small m by capital M plus small m into L. S2 is the actual distance moved by the bigger block with respect to stationary observer on the ground. S1 is the horizontal component of the actual distance moved by the smaller block with respect to stationary observer on the ground. If you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. See the question number 35. This question is also similar to the earlier questions. I have discussed. Here also the man and the platform will consider one system. I think you should be able to solve this problem yourself. Here we consider the man and the platform together as one system. So there is no external force acting on system, because when we consider the man and platform together as one system, the external force acting on system is total weight of system and the normal reaction force exerted by the ice surface on the platform. The platform, then these two forces act in the vertical direction to balance each other. And when we consider the man and the platform as one system, the force exerted by the man on the platform when he begins to move on the platform should be treated as internal force. The reaction force exerted by the platform on the man is also an internal force. So when the net external force on the system is zero, velocity of center of mass remains constant, and total inner momentum system also remains constant. Initially both the man and the platform are at rest, so initial momentum system is zero. So final momentum system, after the man begins to walk on the platform, is equal to initial momentum system. Initial momentum system is zero. Final momentum system is equal to momentum of the man, that is called mass of the man and velocity of the man. Let it be V1 bar plus momentum of the platform. V2 bar is the velocity of the platform. So V1 bar is the actual velocity with which the man moves on the platform with respect to stationary observer on the ground or with respect to ice surface. And V2 bar is the actual velocity of the platform, means V2 bar is the velocity of the platform with respect to the ice surface, which you have to find. So from this you can write small m into V1 bar minus capital M into V2 bar. So the V is the magnitude of relative velocity. So if you consider the magnitudes here, you can write small m into V1, capital M into V2. Similar procedure can also be followed for previous questions also. That means it's all similar to 33 and question number 33, which I discussed earlier, and 32. But I am slightly doing in a different way in the scalar notation now. V1 is the magnitude of velocity of the man with respect to stationary observer on the ice surface. V2 is the magnitude of the velocity of the platform with respect to the stationary observer on the ice surface. So when you consider magnitude, the negative sign can be omitted. When the two velocities are in opposite direction, the magnitude of relative velocity, as I discussed earlier in vectors, will be ordinary sum of the magnitudes of the two velocities, which is given to be equal to V. So I have to solve these two equations. From first and second equations, you can find V2. You get V2 equal to small m by capital M plus small m into V. So V2 is the speed or magnitude of velocity which is which is a platform moves with respect to the ice surface. So that's the answer in terms of magnitude. If you want to copy, you can take a pause and copy. Would like to also show you the alternate way for this problem. You can also follow the alternate method, which is not much different from earlier method. But alternate method means, you can solve the problem in vector form. In vector form, the relative velocity, the man with respect to the platform. So relative velocity of the man with respect to the platform, in vector form we can write V1 bar minus V2 bar. V1 bar is actual of the man, V2 bar is the actual of the platform with respect to ice surface. That can be written as V bar. That means when you solve the problem, you can complete in vector form also. Now you can solve the 1 and 2 equations. To solve the equations 1 and 2, that means you have to substitute the value of V1 bar into the V2 bar from second equation to first equation. Then you get small m into V1 bar, you can write V2 bar plus V bar equal to minus capital M into V2 bar. So if you you can write small m into V bar, you can simplify it yourself also, minus capital M plus small m into V2 bar. So from 1 end we get V2 bar equal to minus of small m into V bar by capital M plus small m. So in vector form, this will be the answer. The negative sign indicates that velocity of the platform with respect to ice surface is opposite to the relative velocity of the man with respect to platform. If you want to copy the alternate method also, you can copy the alternate method. You can take a pause and copy this alternate method, but it's not compulsory. So look at the next question, question number 36. A projectile is fired at a speed of 100 meters per second at an angle of 37 degrees above the horizontal. At the highest point, the projectile breaks into two parts of mass ratio 1:3. The smaller part falls freely from rest. Find the distance from the launching point to the point where the heavier piece lands. Actually, I have discussed a similar question earlier. There are two methods for this problem. One method is similar to the method I have followed for discussion of similar question in the earlier part of the assignment. If we consider the projectile as the one system, that means the two parts into which the projectile splits into as one system. The external force on system is the force of gravity. The explosion takes place due to the internal forces, and these internal forces play no role in the motion of center of mass. The motion of center of mass or path followed by center of mass is only influenced by the external force on system. The external force on system is the same whether the explosion takes place or doesn't take place. The external force on system is the force of gravity, which is the same irrespective of whether the body explodes or doesn't explode. Therefore, the path followed by center of mass of system will be the same irrespective of whether the body explodes or doesn't explode. Therefore, center of mass of the two parts continues to move along the same parabolic path along which the unexploded body would have traveled. Let Kepler denote the horizontal range of the projectile in case if it does not explode. So I choose the horizontal direction passing through the point of projection to as positive x-axis towards right, that means in the direction of the motion. Horizontal displacement of the projectile as x-axis. Vertical upward direction take it as y-axis. Let R denote the range of the projectile in case it does not explode. At the highest point, it splits up into two parts. One of the parts falls vertically downwards. Let M1 be the mass of the first part. The first part falls freely under gravity. That means it falls like a freely falling body from highest point, therefore reaches the ground at a distance equal to, at a horizontal distance equal to R by 2 from point of projection. But center of mass of the two parts continues to move along the same parabolic path along which unexploded body would have traveled. Let M2 denote the mass of the other part. Center of mass system of the two masses M1 and M2 lies in between M1 and M2 on the line joining the two masses M1 and M2. Therefore, M2 will be to the right side of center of mass. So let X2 denote horizontal distance from launching part and from the origin at which the second part falls onto the ground. So the X coordinate center of mass system of the two parts can write M1 x1 plus M2 x2 by M1 plus M2. So X coordinate center of mass when both the parts reach the ground equal to R. X1 you can write when both the parts have reached the ground, X1 can be written as R by 2. Here the two masses are in the ratio 1:3. That means M2 can be taken as 3 times M1. You have to find X2. This you can copy down yourself and try to simplify it yourself. You can take a pause and complete the simplification part yourself. So you get X2 equal to 7R by 6. So you have to complete the solution of the problem. You have to calculate the value of R here. R represents the horizontal range for the projectile in case it doesn't explode. Want to copy the solution of this problem? First you finish copying the solution of this problem. I mean, you take a pause and finish writing the solution, so that I can show you the continuation for this. So the horizontal range for the projectile, in case if it does not explode, is given by horizontal velocity into time of flight. Horizontal velocity is equal to u cos theta. Time of flight is 2u sin theta by g. Of course, you can also use the formula u square sin 2 theta by g. That way also you can do. Here g, you take it as 10 meter per second square for this problem. U is 100 meter per second. Cos theta is cos 37 degrees here. That is equal to 4 by 5. U equal to 100 meter per second. Sin theta is sin 37 degrees, which is equal to 3 by 5. And G equal to 10 meter per second square. Come on, calculate the range R here. So you get 960 meters. As I discussed earlier, x2 will get 7r by 8. So 7 by 8 into 960 meters. This problem was given one of the previous AIEEE entrance exam papers. So we can simplify this. So you check up the calculation. Have done earlier. You are supposed to get x2 as not 7r by 8. Please correct it. You are supposed to get x2 equal to 7r by 6. That correction, please check up the simplification you have done earlier. Here r is 960 meters. You simplify this, you get 1120 meter. So that third option is the answer. See the question number 37. A bomb of mass 16 kg explodes into two pieces of mass of 4 kg and 12 kg. The velocity of 12 kg mass is 4 meter per second. The kinetic energy of other mass is. So the first mass m1 we write as 12 kg. The magnitude of velocity of the first mass just after explosion is 4 meter per second. The second mass m2 I write it as 4 kg. We consider the two pieces as one system. That means the bomb as one system. So here you have to assume that the bomb is initial at rest because you are not mentioned about the velocity of the bomb before explosion. So final momentum of system just after explosion can be equated to the initial momentum of system just before explosion. Because the explosion is caused by the internal forces which play no role in the motion of center of mass. So center of mass of the two parts continues to be at rest. So initial momentum system just before explosion is 0. Final momentum system just after explosion must also be 0. Final momentum system just after explosion equal m1 v1 bar plus m2 v2 bar. So M2 V2 bar equal to minus M1 V1 bar. That means just after explosion, the two parts move in opposite direction with same magnitude of linear momentum. So if you consider magnitudes, you can write M2 V2 equal M1 V1. So M2 is 4 kg, M1 equal to 12 kg, V1 is 4 meter per second. So molecular velocity of these other mass just after explosion 12 meter per second. You're asked to find kinetic energy of second mass here. So kinetic energy of M2 just after explosion is equal to half M2 V2 square. You can copy down. If you are interested to copy down the solution, you can copy down the solution. That will be 288 joules. That's the answer. Okay, I'll continue discussion in my next class.